Welcome to the deep dive. Today, we're tackling something really fascinating that you flagged for us. How our understanding of the brain, cognitive neuroscience, connects with how we learn educational psychology. You shared a great academic article that really digs into where these two fields meet right now and, what we need to be smart about as we try to link them.
Exactly. For a while now, there's been this exciting buzz around the idea that cracking the code of the brain could, revolutionize education. So our goal today is to get to the heart of this. How can what we know about neurons and brain regions actually change how we think about teaching and learning? And just as importantly, what are the traps we might fall into if we get a little too carried away?
Yeah, definitely.
You'll notice the author of this piece takes a thoughtful, maybe even cautious approach to directly applying brain science to the classroom, and that's really what we'll be exploring.
Okay, so let's dive in. The article starts with this encouraging note saying that bringing cognitive neuroscience and educational psychology together is generally a good thing. Then it throws in this term, theoretical reduction. Now, for you listening, this might sound a bit academic, but it's a key idea. What does theoretical reduction really mean in this context?
Right. Think of it like this. Theoretical reduction is about finding the more um, fundamental basis for our observations.
Mm,
In our case, it's about seeing if we can map the things we observe in psychology, like how memory works or why some people struggle with reading onto the underlying neurological mechanisms in the brain.
okay.
And the article makes it clear that in science, this kind of linking to a more fundamental level is usually seen as a path to, deeper understanding.
So it's not just about having two separate lists of facts, one about the brain and one about learning. It's about seeing how they connect at a deeper level, like understanding that the psychological experience of feeling happy might be linked to the release of certain neurotransmitters in the brain.
That's a perfect way to put it, yeah. It's about moving beyond just describing what we see to understanding why it happens at a more fundamental level.
Hmm.
And the article points out that to make this work well between cognitive neuroscience and educational psychology, there's a need for bilingualism. What's the big deal with being bilingual here?
Right. The author emphasizes that for this connection to be solid and useful, well, for you, the educational psychologist needs to be fluent in both languages. They need to understand the neurological terms, what's firing in the brain, and also the psychological concepts, how that translates into actual learning and behavior.
hmm
The article uses reading disability as an example. How does that show why this bilingualism is so important?
Well, imagine you see a brain scan that shows, say, a difference in activity in a specific area for kids with reading difficulties. Okay, that's a neurological finding.
Yeah.
But for that to be meaningful for how we teach reading, right,
Right.
we need to connect that brain activity to specific psychological skills involved in reading, like how well they can sound out words or understand the meaning of what they're reading.
Right.
Without understanding both the brain side and the learning process side, we can't really bridge that gap effectively for you.
It's like saying, this car is having engine trouble, but you don't know anything about how an engine works or what the different parts do. The statement itself it doesn't tell you how to fix the problem, does it?
Exactly.
Now, the article also mentions that for this reduction to really work, the terms on both sides need to be at the same level of empirical specificity.
That sounds a bit like scientific jargon.
Oh.
What's the key idea there for us?
What's fascinating here is the idea that you need a certain level of precision on both the psychological side and the neurological side to make a meaningful connection for you. Think of it like trying to match two blurry images, even if they're both pictures of the same thing. If they're not clear enough, you can't be sure they actually match.
Okay. Similarly, if our psychological understanding of how we learn something is vague, trying to link it to specific brain activity is going to be really difficult and could lead us down the wrong path. The article argues that we need clear, well-defined psychological concepts that we can test and measure reliably before we can effectively link them to what's happening in the brain.
And this brings us to a really important point. The article stresses that we need to have a really good handle on the psychology of learning first before we try to jump to neurological explanations. It uses the story of reading disability research to really drive this home for you. What happened in that field that illustrates this?
Exactly. The article points out that early attempts to use neuroscience to understand, why some people struggle with reading,
Hmm.
they hit some roadblocks. It wasn't that the neuroscience itself was bad, per se, but at the psychological level, our understanding of reading disability was still pretty unclear. Researchers were still figuring out exactly who had a reading disability and what the core cognitive challenges were.
So they were trying to find brain-based answers for something they hadn't even clearly defined in terms of behavior and learning. That sounds like trying to find a specific street on a map when you don't even know what city you're in.
Precisely. The article emphasizes that researchers first needed to figure out who was struggling with reading, using clear ways to identify them, and, crucially, what specific cognitive skills were they lacking? Were they having trouble hearing the individual sounds in words? Were they struggling to connect letters to those sounds?
Hmm.
It was only after we started to get a clearer picture of these psychological characteristics that neuroscience research could become more focused and ultimately more useful for you. Think about it. If you don't know the specific learning process that's going wrong, how do you know which parts of the brain to look at or what brain activity to focus on?
And the article highlights the emergence of the phonological core deficit model. That sounds like another piece of jargon, but how did that actually help move things forward in understanding reading disability?
Right. The development of the phonological core deficit model was a real breakthrough in our psychological understanding of reading disability.
Hmm.
For you, the key idea here is that this model suggested that a primary difficulty for many people with dyslexia lies in their ability to process and work with the sounds of language.
Okay.
This gave researchers a much more specific cognitive target to investigate using neuroscience. Instead of just broadly looking at reading problems in the brain, they could now focus on brain regions and processes known to be involved in phonological processing and see how those might differ in individuals with reading disabilities.
Ah,
Also, as we got better at classifying different types of reading difficulties at the psychological level, it meant that the groups of people being studied in neuroscience research became more similar, making the brain findings much easier to interpret.
so it sounds like having a well-defined psychological theory acted like a spotlight, helping the neuroscience researchers know where to look in the brain.
Exactly. You need that well-articulated psychological framework to guide your neuroscientific investigations.
Mm-hmm.
Otherwise, you could end up with a lot of interesting brain data that doesn't actually tell you much about the underlying learning processes that you're interested in.
Makes sense.
But, as the article wisely points out, even with these advancements, we still need to be careful about immediately applying neuroscience findings to education. The author expresses some caution based on times in the past when we got a little too eager with, quote, premature reductive attempts. What were those all about?
This is where the author kind of pumps the brakes a bit on the excitement. They remind us that the history of our field is dotted with examples where we, well, jump the gun a little bit, trying to apply findings from a more fundamental science, in this case, neuroscience, before we really had a solid understanding at the level of psychology and education.
Hmm.
They even bring up older research from the 1960s and 70s on neuroscience and behavior. For you listening, what's the takeaway from looking back at that older work?
The author is drawing a parallel for you to understand a crucial lesson. There have been periods in the past where there was huge enthusiasm about how neuroscience could transform our understanding of why we do what we do. However, looking back, much of that early work, while perhaps cutting edge for its time, isn't really considered that relevant or insightful today when it comes to complex behaviors like learning.
Right.
The worry is that we might be in a similar moment now, getting swept up in the excitement of brain imaging and other neuroscientific tools without fully grasping just how complicated it is to link brain activity to complex cognitive processes like how you learn in a classroom. It's a good reminder that scientific progress isn't always a straight line, and sometimes promising paths don't lead where we expect.
And this leads into a really interesting part where they bring up this essay called The Psychobiological Silly Season by Bill Uddle. Just the title itself makes you wonder what it's about. What was the main point Uddle was trying to make?
Little's essay, which he wrote way back in the early 70s, makes a really insightful point that's still relevant for you today. He argued that there's this recurring trend in psychology where researchers get incredibly excited about taking findings from neurophysiology, things like measuring the electrical activity of single neurons and immediately trying to build these grand theories about how the mind works.
Ah.
His concern was that every time a new, more powerful neuroscientific technology comes along, there's this temptation to leap to speculative connections between brain activity and psychological phenomena without enough solid theoretical grounding in psychology itself.
So it's like we get a new super high resolution brain scanner and suddenly we think we can explain everything about why some kids struggle with math just by looking at the, pretty pictures of their brain activity.
That's the core of his warning for you. Uttle argued that while it's obvious that our brains are the biological foundation for everything we think and do, the critical question is whether a specific attempt to link a particular psychological phenomenon to a particular brain activity is actually justified based on what we currently know.
Mm.
He cautioned against getting carried away by the allure of new technology and making what he considered to be, well, premature jumps in our understanding.
But the article also reminds us that no serious scientist today doubts that all our behavior and learning is ultimately rooted in the brain. So for you listening, where's the line between making a reasonable connection and falling into this silly season of over-extrapolation?
That's the crucial question, isn't it? The article clarifies for you that the debate isn't about whether the brain is important. Of course it is. The real question is whether a particular attempt to map a specific psychological idea onto a specific neurological finding is warranted right now, given the current state of our knowledge in both fields. The author even suggests that eventually, as our understanding grows, Uttle's caution might seem a bit too conservative. The trick is figuring out if we've reached that point for any given area of learning or behavior that interests you.
And this brings us to this idea of how much the brain actually constrains our psychological theories at the moment. The article quotes some researchers saying that you have to know something about the brain because the brain constrains the nature of the cognition that it makes possible. That seems pretty logical for you, but the author of this article adds a really important but to that.
Exactly. While there is a general agreement that the brain sets limits on what our minds can do, the author's main point for you is that based on our current level of neuroscientific understanding, those limits are often very, very loose.
Huh. Loose constraints.
Yeah. They use some examples from reading research to illustrate this. Take the idea that cognitive neuroscience tells us reading involves things like understanding sounds, meaning, and spelling, and that good teaching combines different approaches like phonics and whole language. What's the author's take on that for you?
Well, they point out that this is a pretty broad conclusion, isn't it? It doesn't really tell us anything groundbreaking that we didn't already know from decades of studying how people learn to read. It's so general that it wouldn't really challenge or change any major existing theories of reading or how to teach it. It's more like neuroscience confirming what we already suspected from observing behavior.
Precisely. For you, the neuroscience findings in this case are consistent with what we already knew, but they don't really force us to rethink our psychological models in any significant way. The author then brings up the examples of surface and phonological acquired dyslexia, where adults lose the ability to read in different ways after brain damage, and also the different types of developmental dyslexia seen in children. How do those further illustrate this idea of loose constraints for you?
They explain that while studying adults with acquired dyslexia, where brain injury affects reading in different ways, did spark a lot of interest in the idea that we might have different routes for reading, like sounding words out versus recognizing them as whole words. These studies didn't actually definitively prove one type of reading model over another.
Okay.
The ongoing debates about these different theoretical ideas are still mainly based on analyzing how people behave when they read, not on hard and fast rules coming from neuroscience.
And the same holds true for the different kinds of reading difficulties that children experience. The author points out for you that the ongoing research and discussions about whether there are distinct subtypes of developmental dyslexia are almost entirely based on looking at children's reading skills and cognitive patterns. We don't yet have clear neuroscientific findings that can definitively separate these proposed subtypes and strongly support one behavioral theory over another.
So for you, the overall message here seems to be that while neuroscience is giving us some interesting pieces of the puzzle, it's not currently acting as a very strong guide or filter for our theories about how we learn academic subjects.
That's the central argument for you. The author believes that right now, the constraints from neuroscience on our theories about how we learn things like reading or math are relatively weak. This leads us to the idea of the two-bridge view of the relationship between neuroscience and education. What is that perspective for you?
The two-bridge view, which the article says aligns with the ideas of another researcher named Brewer, suggests for you that the connection between neuroscience and education isn't a direct one. Instead, it goes through cognitive psychology. Think of it as two separate bridges. One connecting neuroscience to cognitive psychology, how we think and process information, and then another bridge connecting cognitive psychology to education, how we teach and learn in practice.
What's insightful for you here is what this two-bridge model implies. It suggests that neuroscience and cognitive psychology influence each other. Findings about the brain can inform our theories about thinking, and vice versa. Similarly, our understanding of how we think and learn, cognitive psychology, then informs how we approach education. The crucial warning here for you is against trying to make a direct leap straight from neuroscience to education. Why is that considered a risky move?
The article argues for you that this direct jump can lead to oversimplifications and even what we might call pseudoscience ideas that sound scientific but aren't really based on solid evidence. The classic example, of course, is the left brain, right brain myth that unfortunately has found its way into education despite a lack of strong scientific support.
Right, that old chestnut.
Exactly. The author emphasizes that if the link between neuroscience and our understanding of thinking is still somewhat loose, then for the foreseeable future, the most reliable ways to improve education will likely come through cognitive science, which, as we've discussed, still operates largely on its own, guided more by observations of behavior and learning than by direct constraints from brain science.
So for you, cognitive psychology acts as a really important middleman, taking findings from neuroscience and integrating them with our understanding of how we learn before they get translated into educational practices. This helps make sure that any applications in the classroom are based on solid principles of how the mind works, rather than potentially misinterpreting raw neuroscientific data.
That makes a lot of sense.
However, the article does point out one important way that cognitive neuroscience can be valuable right now, even if the constraints aren't super strong. What's that for you?
The author agrees for you that cognitive neuroscience can serve as a useful check on psychological theories that are a bit too vague. Sometimes in psychology, we can have theories that are hard to test or prove wrong, right? Neuroscience can offer another source of evidence that might help us refine those ideas or even rule out some that don't seem to fit with how the brain works.
That's a key takeaway for you. Even if neuroscience isn't yet strongly dictating the direction of psychological theory in areas relevant to education, it can still act as a kind of reality check. If a psychological theory suggests something that seems completely at odds with our basic understanding of how the brain functions, that should raise a red flag.
Hmm.
However, the author also expresses a hope that in the future, neuroscience will become even better at helping us test our psychological theories more rigorously, providing more definitive evidence for or against our ideas about learning.
And the article wraps up by saying that the author's own view is one of cautiously accepting what we learn from neuroscience. They see it as one piece of a larger puzzle, along with evidence from lots of other research methods in cognitive science. It sounds like they're not saying neuroscience is useless, but rather advocating for a more careful and integrated approach for you.
Exactly. For you, the author is emphasizing that within this idea of being cautiously open to neuroscientific findings, there's still plenty of room for discussion about just how strong the connections are between these different levels, brain, thinking, and behavior, and how soon we can expect to see really direct and smooth applications of neuroscience to the world of education. It's an ongoing debate.
So, to sum up our deep dive for you, while the connection between neuroscience and education holds a lot of promise, and it's definitely important to be able to speak both brain language and learning language, it seems really critical that we have a solid understanding of the psychological processes involved in learning first. We need to be careful about jumping to quick applications of brain findings in the classroom. And right now, it seems the brain isn't giving us really strict rules for how we should be teaching. The most effective path to improving education might just be built more carefully through our understanding of how we think and learn.
And that leaves us with a really important question for you to think about. Given all these complexities and potential pitfalls we've discussed, what are the most responsible and effective ways for educators and researchers to engage with findings from cognitive neuroscience moving forward? Should the primary focus be on using neuroscience to better understand the fundamental processes of learning, with applications in education coming more indirectly and with careful consideration? It's definitely something worth pondering.
Indeed. Thanks for taking this deep dive with us into this fascinating area. We'll catch you next time.